Oh, I didn't know.
Hello, everyone. Welcome in. We're just going to give a few more minutes for everyone to join, and we'll go ahead and get started.
We're just double checking. You can see my screen, right?
Yes.
Okay.
Give another minute or two here, and we'll go ahead and get started. Welcome to all who have joined so far. Happy to have you. All right, everyone, let's go ahead and get started. I am Will Azar, Strategic Marketing Engineer here at Efficient Power Conversion. Welcome to today's webinar, designed with GaN power electronics for high-fidelity Class D audio for a better listening experience. Before we get started, I would like to go over a few housekeeping items for today's event. You have the opportunity to submit text questions to the panel by typing your questions into the Q&A feature at the bottom of the screen. Please use the Q&A feature rather than the chat feature. You may send in your questions at any time. We will collect them and address them during the Q&A session at the end of today's presentation. Now, I would like to introduce our speakers today. Josh Fang is Senior Director of Strategic Product Marketing at Efficient Power Conversion. Josh has over 16 years of experience in the power electronics industry in product management and applications engineering. Also with us today, Tiziano Morganti, and Senior Field Applications Engineer at EPC with over 16 years of experience in power electronics and audio applications. Josh, thank you for joining us today. Let's get started.
Thanks, Will, for the introduction. Hopefully everybody can hear me loud and clear. Good. My name is Josh. Together with Tiziano, we're gonna spend the next 45 minutes to share with you what Class D audio's kind of market overview, the challenges, and what the solution that we can potentially bring in to solve those problems. And here's the agenda we're gonna be talking through. Started with, like I said, audio amplifier market overview, the challenges that we've been seeing for the last 2 to 3 years, and the audio amplifier requirements, and how Gallium Nitride, especially from EPC, can enhance Class D audio in various different ways. And then we finish up with a summary. All right, let's get to see how the market looks like. For people who are in the audio space, I think I'm seeing some familiar faces here. Three big segments are basically the home audio or consumer audio, followed by professional audio and transportations. Home audio space, as you see, there are many different type of applications down to very low power, smart tablet, smartphone, PC, the high power mini combo system, or this hi-fi amplifier solutions. In the professional audio space, well, it's mostly more high power active speakers, line array, touring amplifier, constant voltage amplifier, or prosumer guitar amplifiers. And on the right-hand side is the transportation, which cover aftermarket car, boat, ATV, or even OEM car audio amplifier space. Among all three, we're seeing there are a lot of different power spectrums. What we play a little more most is in the mid to higher power range. For example, pick home audio, for example, subwoofer or multi-channel soundbar, professional amplifier, mainly high power application, mid to high power application. Transportation space are also mainly, especially aftermarket space, and some high-end premium car audio that also in more of a higher power, mid power range. And the interesting thing is we've been seeing the last 2 to 3 years a faster adoption in gallium nitride technologies, starting from home audio, professional audio, and transportation audio. Home audio, there's some big names, for example, Technics, Sony, and other big companies are starting releasing products, high-end products with a GaN inside. And professional space as well, especially for those multi-channel installation amplifier, people do see the power density as a key ingredient to really shrink the form factor. And transportation, car, boat, as well as many other customers right now are looking into a GaN solution to enable a higher power density. However, within all this fast adoption, there are challenges that in this audio community in the last 2 to 3 years. Especially, I think people heavily in design, in product development are aware that silicon or semiconductor supply is a huge constraint during the COVID pandemic period, which end up the R&D team spend a lot of time, too much time, actually sometimes too much time on redesign rather than coming up with the breakthrough innovations or better ideas in the last 2 years. And there's a couple of challenges if you kind of break it down by different power level. On the low power size, 100 watts and below, we're seeing some portable device demanding longer playback time. Some Adobe Atmosphere has also enabled more channel in a soundbar applications. And of course, those are consumer applications, so price are definitely always a bit sensitive in those arenas. However, as you go to mid power, typically 100 to 300 watt per channel range, thermal heat sinking become more of a critical items and require engineering attention to when they do a designs. And sometimes I heard from the customer is lacking of I2S input amplifier solutions with the dynamic range control. It's something that they wish to have more solutions out there in this particular mid power space. Now, at the higher power, especially 300 watt or even higher, thermal heat sinking pretty much is a must-have. It takes a lot of space. It's not very desirable when you need to have a compact industrial designs that often give you just one more dimension of constraints. And the second point is, higher power typically translate to higher voltage. Tatiana will spend a little bit more time on that later, especially when you go above 100 watts. 100 volt switching device, they don't often count very good figure merits. There are a couple of tricks you need to do. For example, parallel upper stage switch to enable longer playback time, longer audio power durations. However, parallel upper stage switches it's quite common. However, it has its own drawback. It makes your audio switching parameter worse. Which is make the design more complicated. And of course, dedicated audio controller is quite rare in this space. So that added one more dimension into a design challenge in a higher power space. What our solution mainly help out with the mid power. Our initial offering will be more helping out the mid power and high power arena. That's where we see the most value add in those applications. And if you ask what do we anticipate, where do we participate? In terms of audio amplifier, as we know, it's it's basically audio input signal from comparator OTA to a PWM input, and the PWM input will drive the power output switch to magnify the voltage, the PWM signal at the output stage at the switching nodes, and eventually low pass filter would translate to a more of an audible bandwidth. And the end goal is to drive the loudspeaker efficiently, right? And while our initial offering is to focus on the power stage, especially on the upper stage switching sessions. However, Class D audio comes with different topology, and Tiziano will spend a few minutes in the next couple of slides to go through the topologies and requirement with you guys. So Tiziano, go ahead.
Yep. Welcome to the webinar. Basically, the main topologies that are used to implement the power section of the Class D amplifier are either the half bridge design for a single-ended output stage, or the full bridge topology, which can be also operated with a single ray power supply, while the half bridge is definitely requiring a dual split power supply. Recently, also a multi-level approach has been introduced, and this can have some advantages in terms of reduction or elimination of the output filter. But it has also drawbacks, especially in terms of crossover distortion from one level to the other transition. Next slide, please. Okay, so when you need to design a Class D amplifier product, the first question that is coming is always, what is the power that I need? And this also comes with the definition itself of rated power. So the rated power definition is maybe the topic for a specific webinar, because it depends on the application, it depends on the standard that needs to be used for the measurement of the power. But this is the most important parameter. Then the audio performance need to be there. So basically idle noise, distortion, intermodulation distortion, and the power bandwidth to operate a full bandwidth loudspeaker. So 20 to 20 kilohertz, or even extended to 40, 50 kilohertz. And lately, I mean, the last years, it is recognized that Class D amplifiers can achieve high performance, so they are fitting most of the applications, if not all of the applications. And then the differentiation factors, so basically how much heat is generating the amplifier to operate. And so this is related to the losses, and we are talking about mainly idle losses. So when there is no signal output, or the amplifier is delivering very low power. And this is really important, because most of the lifetime of an audio amplifier, the condition is idle, or maybe background music, so very low level. So having low losses in idle is really important. And also the rated power efficiency. And this is important to design correctly the thermals of the product. So basically how much heatsink I need, or if I need ventilation, and what's the airflow that I need to dissipate the heat. And finally, size of the amplifier section. So this translates into how much PCB real estate I need, or if I can use shallow components for a compact design. Next slide, please. Okay, this is a table. We are not going in detail, but basically it's an example of requirements for Class D audio amplifier design. And so we are, of course, specifying the power on various rated loads, so 8 ohm, 4 ohm, 2 ohm. And also we are specifying the maximum voltage, current, frequency response, and so on. So basically highlighted are the most important, so output noise, efficiency at rated power, idle losses, and so on. Next, thanks. Okay, so basically, how can I select the right device to implement the power stage of an audio amplifier? So from the rated power or from the maximum peak voltage I need to achieve, I can pretty easily choose the VDS ratings of the switching device. So basically, if it is an half-bridge topology, I require a VDS rating of 2 times the peak voltage plus a margin. The margin includes both the margin on the VDS ratings itself, and also it accounts for some voltage drop that is allowed on the power supply during the power burst. For full bridge, it's similar, but it's, of course, it's not 2 times the peak voltage. It's just the peak voltage plus the margin. So it can be seen that for medium to high power amplifiers, it is easy to require a 150 volt or 200 volt rated device. In terms of selection of the device, you need also to allow for the peak current to be handled, and the device needs to sustain the losses during the peak power or the burst power. So this is not trivial, because when you select the RDS on or the thermal parameters of the device, there are other parameters like the gate charge, the output charge, and especially the silicon MOSFETs. It's really tricky to find a device with a good body diode behavior. This means both losses and robustness of the body diode. So basically, what happens usually is that devices that on paper looks good then are tested and they fail, or they generate too much losses. And this involves a fair amount of trial and error to find the right device for the application. Next, then.
Yeah, so Tatiana, yeah, exactly right. I think when once you get down to the voltage part, it's quite straightforward. However, all the secondary parameters become really tricky, right? And you can actually parallel the RDS on. You can do different modulation tricks. However, all this require quite a bit of trial and error, and having many engineers working in the lab to figure out the problem and to solve it. And what we're thinking is, what about if it's just there is a solution that is a fundamental solution, that's just a better switch, right? A switch that can provide much better losses, lower losses compared to any solutions, silicon solutions out there. That's 4 to 10 times lower losses, small heatsink or no heatsink at all, and that there's a heatsink removal benefit in terms of size, compactness, in terms of cost, BOM cost. And if for any application that does require a fan, and you can also tune down to lower speed, reduce the power requirement for the power supplies. And the fundamental switch, a better switch that can switch a much higher switching frequencies that enable maybe a smaller or less expensive inductor, especially at a low pass output filter, and also allow a better control loop that can enable some of the very advanced modulations designers do different type of tricks. And last but not the least, a switch that can have a clean switching waveform, eventually kind of translate to a better audio quality and almost ideal switch waveforms compared to silicons, and better open loop linearity. And if I were to kind of take an example of more of a typical high power silicon MOSFET solutions, let's take 200 volt as example, 4227. It typically comes with a D2 bag, a pretty beefy package, D2 bag or TO220 in the device size range of 150 millimeters square. And typical RDS on ranges are like 20 to 25 million ohms. Yeah, this is kind of a popular solutions out there. In order to even deliver higher power, if a current or thermal become a constraint, typically it's mostly using as a parallel configurations. However, what about if there is just a better solutions in all space, in all spec, all parameters? And here go, I think we have a way to get there with EPC GaN solutions. For example, I'm gonna take the right-hand side, 230204, sorry, it's a QFN package. 7 times better audio sounds, 10 times better in QGD, 3 times better in QG, indefinitely better or 0 QRR, reverse recovery charge, and 10 times smaller. Typically, when you have a magnitude better or 10 times better in any given generation, that technology typically can really make some big major difference. In this particular case, 10 times smaller, 7 times 1/7 that RDS sounds, no reverse recovery, and even enable a higher switching frequency from traditional 200, 300, potentially can do 800 kilohertz, 1 megahertz switchings. However, you might ask, okay, great, the parameter looks good, it's 10 times better. So what is that really translated to audio or Class D output stage? Output, we have a different audio output power. You have, full power, 1/8 power, 1/3 power, idle power. What does that really mean to us? What does that really mean? I think Titiano had really nice put one table that can further elaborate what the system level benefit all this GaN device can bring into our designer community. Titiano, why don't you spend a few minutes here?
Yeah, basically, let's consider some of the working conditions for the output stage of Class D amplifier. So let's get the example. So 70 volt peak, 30 amps peak amplifier. So this is 625 watts on 2 ohm rated amplifier. So let's get the first row of the table is the worst case condition for the output switches. So basically the top of the sine wave. So high voltage, which means high duty cycle, 95% in this simulation, and together with the maximum current, so 30 amps. So in this condition, it's carried out at 125-degree junction temperature for both the silicon MOSFET and the 2215. So you can see conduction losses are 40 watts for the silicon MOSFET and are less than 1/4 for the gallium nitride FET, the EPC 2215. So 9 watts against 40. And this is just because of the lower RDS on. When it comes to the switching losses, the switching losses are 3-4 times lower because of the faster switching. But what is really real difference is the losses associated to the body diode recovery. So with silicon MOSFET at high junction temperature, the body diode is really having a lot of charge to be recovered. And let's say a practical number for the losses of this device is about 40 watt of losses, switching at 200 kilohertz and with 30 amps current. So basically, we don't have a parasitic body diode. We have no junction in our devices. We have no body diode. We have 0 recovery losses. So these 40 watts just go away. And also, if we translate down to, let's say, sine wave output, continuous sine wave output, this is providing the same amount of loss reduction, basically. So an example, so we go, let's say, from 90 watts for the silicon MOSFET in the worst case condition to 13 watt, and this is the loss in the worst case device. If we consider the idle losses, that's another important figure of merit of the amplifier. It's not only the reduction of the conduction losses. So basically, this the idle losses are taken with the amplifier operated in 0 voltage switching. We will see in the next slide. So basically, there are no switching losses. There are low conduction losses because this is just related to the ripple in the inductor. But what is there is the gate drive losses. So with silicon, we have about 10 times more gate charge to be driven into the MOSFET. And also the gate drive needs to be 10 volt, 12 volt. With the EPC GaN FET, we have about 10 times lower gate charge, and the gate drive is at 5 volt. So basically, we save a lot of power in the gate drive losses. So summarizing, about, let's say in this case, 400 kilohertz switching, more than 1 watt, so 1.3 watt of saving. And this is really making a difference in terms of thermal design. So if we compare a long-term rating of 1/8 of the power, it's 8 watts to be dissipated in the heatsink for each channel of the amplifier against 1 watt. And this is a real benefit because it can allow much easier heat sinking of the device, very low airflow if not really convection cooling. Okay. Next. Okay. Some words about the idle losses. So basically, the optimization that is made is to reduce the idle losses at the minimum level is to set the dead time of the output stage to the right amount of time that is required to flip the switching node from one side of the power supply to the other side. And this is done by the current ripple in the inductor. So basically, there is an optimal setting of that time that minimizes the losses in the output stage. Of course, you can trade off some of the losses to reduce the dead time and achieve a better THD. So basically, maybe the saving on the gate drive losses can be traded off for a better performance lower THD amplifier, or vice versa. Sometimes it is set a longer dead time. The THD gets a little bit worse, but the 0 voltage switching operation is extended to higher. Maybe up to medium level of the power of the Class D amplifier. Okay. Related to the switching waveform for a gallium nitride half bridge, basically we have 2 factors that improves the let's say the quality of the waveform. Basically, one aspect is that the switching times are much smaller. And usually also the gate drivers have tighter specs on the timing, and this allows smaller pulse width distortion, so smaller jitter in the rising edge and the falling edge. So you can see here a typical silicon device switching node waveform. So there is some hesitation because you need to recover the charge of the body diode. And then there is some snapping that is usually causing some ringing. And also the bigger package is getting towards the parasitic of the power loop, the power loop inductance. So you can have yes, lower frequency ringing, but with significant higher energy. So also the EMI can get worse. With the gallium nitride FETs, you can guarantee a faster switching, but the lower power loop inductance really minimize the ringing of the waveform and improves the linearity and reduce the pulse width distortion. So this can provide a better open loop linearity of the amplifier. And this in turn translates into a lower THD figure when you close the loop. Okay.
Good. Yeah. Thanks, Tiziano, for sharing the technical content. And I think here we'll highlight that this is also kind of enable open loop. It's not one of few of designers that have they can actually do open loop design. And if any of the audience are interested, we can contact us. We can definitely make a referral to the design community who have a specialty on doing open loop design. Okay. And we talk about now the device level benefit in terms of silicon MOSFETs, and how does that translate to system level saving and the system level benefit on especially on the Class T output stage. Then the next question is okay, what does EPC have to offer? And this is kind of our latest generation 5 portfolios. They are discrete gallium nitride switches. And kind of the highlighted greens are the one that we kind of recommend the most, especially for higher power audio amplifier designs. Go down like, for example, and then typically those highlighted green are like a 10 milliohm device or 10 milliohm audio sound or lowards. Again, it depends on your output power requirement and how do you rate it, the powers. If you need to be a system at much longer time, you might need better thermal management and kind of translate to a better audio sound device. However, if it's more of a peak output power requirements, really the voltage will be the limitations. And within all this, with all this offering that we have, typically we'll recommend customers are 100 volts. This is a CSP package, so 100 volt, 170 volts, and all the way up to like 200 volt device. And you might ask, what is the kind of the power translate? How does that translate to audio powers? And here, if you put it into like a half bridge or single ended configurations, 2052, for example, can probably do 100 watts at 4 ohms, and the 170 volt device will be able to deliver about 300 watt to 4 to 8 ohm speaker impedance, which is actually quite common for like subwoofer, home subwoofer applications. If you require even higher power, typically you have to increase the voltage. Then 2215, 2007, this particular one can do about 600 watt at 4 ohm. And of course, if you want to further, you want to drive higher speaker impedance, and also deliver more powers, then you also have can adapt the topology of BTL, bridge tie low, to further increase your output powers. For example, from 100 volt to 400 watts, 200 volt can do as much as, for example, 1.2 kilowatts at 8 ohm. Now, those are CSP packages out there. We also have a family of a QFN device, which is a little bit easier for assembly purpose. What we are offering here is basically called a 230X family. They are exactly the same footprint compatible. They are all in a 3x5 millimeter, 3x5 millimeter size, which means about 15 millimeter square. And we have offering in 100 volt, 150 volt, as well as 200 volt. And each voltage node has kind of one that have optimized for the best audio sound, and one more like a half size audio sound range where customer really want to, they want to switch maybe, for example, higher switching frequencies and better switching parameters. They can definitely choose the half size flavor. And what we kind of recommend for the higher power are the 2308, 04, and 07. And you might ask again, how do you translate to kind of audio powers? And here we go. If we plot it to more of a half bridge or single ended configurations, 2304 can do about 800 watt, 2 to 4 ohms. And if you want to design in a more of a BTO configuration or 4 bridge configuration, it can deliver about 2000 watts at 4 ohm. All this flavor, all the samples are available today. 2302 is the first one that's already released in production last year. The remaining one will be released toward the Q1 or end of this year, beginning Q1 2024. So those we talk about CSP as well as QFN package that can really deliver higher power and higher power density in audio space. We also, for slightly different, covering different application, we also have a power stage integrated IC that integrate gate driver together with one high side and one low side switches. Today we come with a flavor of 100 volts, various different audio sound and output current. Those are more of a RMS continuous current. And the target applications are like, for example, buck boost converter, buck converters, ALC converter, motor drive, and one of the applications, not so much a very high power, 500 watts and above, more like I would say 100 to 300 watt range Class D audio amplifier. This could be an area this can make a design a little bit easier because it does integrate the gate drivers. So last layout headache there. And as we go more even higher power, for example, we also have here's kind of our recommended, or the gate driver we have been working with is basically our controller and gate driver ecosystem partners who has a more compatible gate driver that can work well with our GaN device. I will share, I'm not gonna go through this in detail, but we're gonna share the slides so you can take a look as you wish. Last but not the least, is right now we are in kind of the design phase. We are ramping out this EPC GaN Class D evaluation board that's highlighting 1 kilowatts per 4-inch square. And that comes down to really this power stage, for example. This power stage is about 5 centimeter or 2-inch by 2-inch. This block itself can deliver about 1,000 watts at 4 ohm, 700 watt at 1,000 watt at 2 ohm, 700 watt at 4 ohm, and roughly about 450 at 8 ohms. We think this is power density will be very strong value added, especially we're gonna target to shoot the heatsinkless and let's see how it goes. You might require a little bit of PCB coolings for this particular design. But for the majority audience, this particular evaluation platform is not going to be a turnkey product. This is more of our EPC evaluation platform to enable the audio design community so that you guys can scale out your design faster. And number 2, validate the benefits of GaN solutions. And maybe Tiziano, do you want to share a few words about this particular design?
Basically it's I think you already said what's important. Let's say we focus on the QFN devices because this can be maybe scaled to other voltage or current ratings just by replacing the QFN device with one of the other of the family.
Yeah.
And basically we have this pluggable modulator board in order for engineers in the lab to maybe design its own modulator and see what happens maybe at different running frequency. So this board will switch at about 700 kilohertz, and maybe there is some customer that wants to see what happens at higher frequency, and I mean they can plug their own modulator. And so basically it's really something that is flexible enough to be useful in the lab. But you can also, let's say, take the schematic and the PCB design and squeeze in a single board and design your own, at this point, much smaller than this implementation.
Yeah, well, yeah, thanks for sharing. And we're kind of designing a way, hopefully it's AP audio precision equipment friendly. You can just plug it in, you know, XLR, plug in RCA, and then you can measure the performance right away. Okay, and then that's kind of the last slide we want to share with you guys. In terms of, I will quickly run through the summaries. What we discussed from all the summary from what we discussed earlier, GaN adoption has really speed up for the last 2 years, especially in the audio space. You know, the funny thing, if I add one more point as a reflection is, you know, vacuum tune was taking place in the early 1930s. BJT took over place in 1960. MOSFET took over place in 1990s. And the funny thing is, it's all about 30 years apart. Now, if I add 30 years to the 1990s, that's translated to about 2020, which is kind of coincident to what we've seen for the last few years adoption in audio space. Number two, we have 80 plus device out there. We have, in terms of mid voltage space, EPC, we have the widest audio GaN solutions offering. So you won't be stuck with just one audio sound or certain switching parameter. You have quite a variety of, for example, 2 million, 5 million, 10 million, 50 million device, kind of tailored to what's the best solutions for your design. And we hope to drive is to offer a very fundamental advantage to augment what the audio designer, for example, you guys, do what you do best. And there are a couple of different items, right? There's a power density, audio performance, audio power, or some people just want a very compact industrial designs. We believe we offer a fundamental key ingredient to enable what you guys do best. In terms of what we're offering, basically, we strive to achieve product differentiation 10 times better figure of merit than any silicon MOSFET device out there. And integration is also part of our journey to success. For example, first path is power discrete device. Next is integrated gate drivers. And also, I mean, we're not gonna be able to do this alone. We have many different partners. Either they are controller partner, driver partners, or even module partner to empower the audio design community so that you guys can bring, for example, this device, this particular technology to really make your device, your system better, attract more end users. Last but not the least, reach out to our technical expert if you want to learn more about our GaN solutions. And here, my last slide kind of just summarize kind of a couple of different contact points that you can contact us. If you want more like a face-to-face, want to be on the phone, conference call. The first link basically is a summary of our FAE sales field team contacts. And if you feel like you're more of a tech forum type of guys or girls, you want to look for information on yourself, study on your own. Here you go. We have a tech forum of a full wealth of technical content that you can ask, and we will have expert to answer your questions. Last but not the least, what about if you just have a device, for example, silicon MOSFET device or Gallium Nitride device, you are designing and you feel like, I want to see what EPs have to offer in terms of cross-referencing. There you go. The last link is basically our cross-referencing tool. Enter your device, and it will return a cross-reference from EPC solutions based on a set conditions. And you can also alter, for example, Class D audio is more like a 50% duty cycle instead of a 20% duty cycle from buck converters. You can alter the switching condition to meet your need in order to find a better cross-reference. That's it. Will, stage is back to you.
All right, thank you, Josh. Thank you, Tiziano. Now we're going to begin answering the questions submitted during today's presentation. As a reminder, you can still submit questions by typing your questions into the Q&A feature at the bottom of the screen. So we have a lot of questions, so let's get to it. Our first question here is there any limitation to use a high voltage EGAN VDS of 150 to 250 volt and low voltage application up to 20 volts?
Yeah, okay, I can take it.
Sure. Go ahead.
There is no limitation. It's just it's depending on what you need to achieve. So basically, it's not optimized. It's not optimized in terms of cost and device size, because but basically the GaN FET is I mean it's a FET, so it's a variable resistor that is controlled by a voltage between gate and source. So it can switch from a millivolt to the rated voltage of the device. So there is no limitation in the application. It just is not optimized.
Yeah, and maybe if I were to add one more flavor in there, if it's a 20-volt applications, well, we do have 40-volt GaN device that's a little more cost competitive. I mean, versus a 150 volt or 200 volts, and it comes with a flavor. I think 3 milliohm, and soon we'll have another version of higher RDS ons. And if that's the direction that you want to take, and if it's 20 volt, for example, from the power supplies, I would say maybe 40 volt is probably sufficient enough in terms of the power range. Because at the end of the day, the power is limited by your voltage, right? Higher voltage device, 150 volt, 200 volt, it looks great, but then it might be a little bit overkill. So in terms of if the decision is going for GaN, I will probably recommend more of a 40 volt device.
All right, thank you. Our next question is, for properly sizing the GaN device, for example, selection of EPC 2215 for peak power of 20 ms test, what is the maximum dissipation that is allowed in the GaN FET for that 20 ms event?
Okay, maybe we can return to the slide with the table of the power losses.
Yep, sure.
Yeah. Okay, so basically the worst case is the crest of the sine wave. So if it's maybe a 20 hertz sine wave or maybe less, it's going to have 20 millisecond duration. And then we need to dissipate about 13 watts on the EPC 2215. So basically what is required is a good thermal design for this device. It's a small device, it's about 7 square millimeter. So it's a small device. You need to implement top side cooling. So basically the junction to top thermal resistance is really small in our device. Then you need to apply an high conductivity thermal interface material, soft gap pad. And then you need likely a small heatsink or a small heat spreader. And this will take the heat out from the device from the top side. It is not negligible in this short duration of 20 milliseconds. Also the thermal dissipation from the bottom side of the device, so to the PCB. And for this is important to implement a PCB with likely a 2-ounce copper on the top layer, or with using vias in pad plated over technology. So it's quite a standard technology. It's not adding much cost to the PCB. And in this case, it is recommended to place as many vias are possible to fit directly in the pads of the device. And this will take the 20 millisecond power loss from the device also to the PCB, and this will add some inertia and basically will solve the problem. So it's possible to dissipate this amount of power about 15 watts for 20 milliseconds in this case. It's more or less the same challenge as the silicon device. It's not better, it's not worse. The device is much smaller, but also the power dissipation is 7-8 times lower. So it's the same, let's say, challenge.
Good. Thank you very much. Our next question is, what about external anti-parallel silicon diode and D-class? Is it mandatory to use with eGaN?
It's not mandatory. We recommend a small Schottky diode, and you can find small ones in the 200 volt voltage ratings. It can be used to reduce the losses a little bit, because we have a reverse conduction mechanism. So we have an equivalent diode which is dropping in about 2.5 volts, and it has no recovery. And this 2.5 volt of drop is adding some losses during the freewheeling during the dead time. And so we recommend to place a small, it's not mandatory, but we recommend to place a small Schottky diode which takes just the current for the few tenths of nanosecond of the dead time. And this will also improve the linearity of the output stage, and will remove some of the losses from the GaN FET. This is what we recommend. But it's not mandatory. It's a trade-off that you need to do. Can be also that it's just shorting making the dead time shorter, and reducing the losses on the reverse conduction by just having a shorter dead time.
All right. Let's see here. What GaN FET driver is on the evaluation board? Also, what are the PWM controllers or circuits on the eval board?
Okay, the gate driver is a non-semi part, which we found to be very effective. It has some nice features, like the integrated low dropout regulators on both the floating driver and the low side driver. And this allows to provide a higher voltage and to have some tolerance on the drop of the floating gate driver supply voltage, because with the class D audio amplifiers, they need to run at the extreme of the duty cycle, so they need to run at also 100% duty cycle for few tenths of milliseconds during clipping. And so this feature of the on-semi driver is useful to achieve precise gate drive voltage of 5 volt, also with the bootstrap supply for the high-side gate drive. Related, what was the PWM controller also? PWM controller, it's discrete implementation, so like op-amps and comparators, and it will be published. So when the eval board will be ready, it will be also published the schematic and the layout. We can also share the design files. We use Altium for designing our eval boards, so it can be a good starting point for design.
And then a follow-up question to that is, when are the evaluation boards available?
Yeah, right now we're looking at about Q2 this year. So that'd be more starting by April timeframe.
We have another question here. Hello, I am using the Infineon IPPO51N15 and 5 and MOSFET for our motor driver application, which has an RDS(on) of 5 milliohms and QRR of 83 NC. What is the major benefit of GaN over this device, which doesn't require a special driver?
Yeah, this is a motor drive. So it depends on the target switching frequency. Usually motor drives are switching at lower frequency, but we have, I think we have dedicated webinars for the motor drive benefits, but one benefit by sure is going to be more compact because our devices are smaller size, smaller physical size. And depending on the motor, you can get benefits at system level if you run your PWM frequency at maybe 100 kilohertz instead of 16 or 20 kilohertz. So in this case, you can save losses in the motor because of the lower ripple. And it really depends on the choice of the switching frequency. But when you move to higher switching frequency, then it can be done with GaN because the switching losses are really small. It's not always possible with silicon devices.
All right, moving along here, we have still quite a bit of questions, so we're probably not going to be able to answer all of them with the time allowed, but our next question is package EPC 2215 light sensitive? What is a surface material? Is it transparent, epoxy, resin, or SiO2?
The device is, so if you look at the device from the top side, so when it is assembled on the PCB, the top side is silicon substrate, and it's not sensitive to light. So basically, it's I think it's passivated silicon. So it's not light sensitive.
Yeah. No.
There is on the bottom layer there is Kapton tape because the active region is on the bottom layer. There is a Kapton tape to protect the metal layers of the device, and then there are the solder bumps, which are lead-free solder alloy.
All right, our last question here. What valve bias supply regulation margin do you recommend? I am interested in using multi-output winding bias supply to save cost, but it make isolated valve regulation worse.
Yeah, this is a good question. So basically, so floating power supply to operate the gate driver, the floating gate drivers. Let's say that we require quite a tight range for the gate drive voltage. So we specify usually 4.5 to 5.5 gate drive voltage. Can be extended a little bit, but not too much. Let's say that we recommend 4.5 to 5.5. And this is quite a difference with silicon MOSFETs, because you can, let's say, go around them, let's say between 8 and 18, and they are fine. So for the floating power supply, the real difference is that we require about 10 times less power to operate the gate driver. And what I recommend is to have a higher floating voltage with a small low dropout regulator that regulates to 5 volts, or even if depending on the trade-off of the, might be also like just a Zener shunt regulator. This is
All
my
right.
recommendation.
Well, thank you very much. We had a lot of questions and we weren't able to get to all of them. So thank you, Josh, Tiziano, and everyone for attending today's webinar. If you did not have a chance to answer your question, you can reach out with over to info@epc-co.com. Please send your additional questions there. We will be happy to answer them. Again, that is info@epc-co.com. You'll receive a follow-up email within 24 to 48 hours with a link to a view of the recording of today's webinar. Lastly, be sure to register for the remaining webinars in the GaN for Consumer Application series. Next installment is next week, February 22nd, and the topic will be on designing with GaN power electronics for smaller, more efficient USB PD 3.1 fast chargers. Please visit our website at epc-co.com for more information and to register. Thank you for joining us today and have a great rest of your day. Take care.
Thanks, guys.
Thank you very much.
Thank you.